Hello students, this is our lecture number 15 and today we are going to discuss very important topic of process synchronization, that is Peterson solution. So from our previous session you have basically understood the importance of the data inconsistency problem and what should be the solution or the criteria for the solution to it. So and what is the meaning of rest condition and how does this data inconsistency problem arises. And so today we are going to discuss about the solution to the critical section problem, and the solution is basically a software based solution. And before the evolution of the complete solution to the software based solution, whose name is Peterson solution, how it has evolved over the period of time, that I am going to cover it up. So in addition to that, that is basically the algorithm 1, algorithm 2 and algorithm 3. Before discussing that, there are two technical terms very commonly used in process synchronization, namely busy wait and spin lock. So those two are very important key terms that it is necessary for you all to know, which I'll be covering up through this session, right? Okay. Now, just to give you a glimpse of what is all about the Peterson solution. So, Peterson solution is a software-based solution to the critical section problem, which satisfies the criteria for solving the problem, namely bounded waiting, progress, and mutual exclusion. Right? Okay. Now, this Peterson solution has some problem. The problem is that the solution is only restricted to only two processes. So if in a system there are only two processes, and in that kind of scenario Peterson solution works. Another important term that you need to understand through this slide is the atomic operation. So what is the meaning of atomic operation? Atomic operations are the operations which cannot be preempted or interrupted. For example, suppose you are executing any instruction like A equals to B or B equals to C, or any load or restore instruction. Load or restore instruction means, load means you are trying to load the data from the computer memory, or you are trying to store the data into the computer memory from the variable or the register. So these operations are assumed to be an atomic operations which cannot be preempted once it start executing, right? So this is this is an atomic operation, and it is an assumption. Here we make it that whenever you try to perform a load or store instruction, it is an atomic instruction which cannot be preempted or interrupted in between. Okay. So the solution, Peterson solution, basically uses two different variable, turn and flag variable, which has its own meaning, which I'll be covering up in few upcoming slides through the examples. So it has got its own significance, right? So I'll discuss later on. So based on these two uses of these two variable, turn and flag variable, the solution is provided, okay, in different algorithms. So I'm going to be covering up in a few upcoming slides. Now, just to give you a summary of it, what is all about the critical section, solution to the critical section problem, the criteria for criteria for solving the CS problem. Okay, so first one is the mutual exclusion. So mutual exclusion, in short, whenever there is a process. So in all these three examples, the three criteria, I'm going to take help of the two process only for convenient explanation. Suppose there is a two process in the computer system, and I say that it follows the mutual exclusion. Means that whenever there is a process Pi which is currently executing the critical section, so at that same time Pj cannot be executing in the critical section, right? So this, if this criteria or scenario is satisfied, that scenario is known as a mutual exclusion. Next is the progress. Whenever there is a process who is currently executing the critical section, and there is another process Pj who is not executing the critical section, it may be in a remainder section, and do not want or do not wishes to re-enter the critical section, then in that situation it should not influence the other process who want to enter into the critical section. So the decision who will be entering the critical section next cannot be influenced by another process, and this decision has to be taken in finite amount of time. Finite means as quickly as possible, right? Now coming to the point, bounded waiting. Bounded waiting means whenever any process want to enter into the critical section and has made the request, but unfortunately that request is not granted because some other have got the preference, other process have got the preference to execute the critical section. So in that case, the requesting process has to wait for a maximum of uh, for one process to complete it. Okay, so basically in short, the waiting of the process who wishes to enter the critical section cannot be waited for unlimited amount of time. There should be a limit. So this is all about the criteria for the CS problem. Now we'll try to understand the concept of spin lock. So what is a spin lock, or what is the meaning of Bezier? So that we'll try to explain with the help of the example. Suppose there is a person. Okay, so there is a two person. So this person name is person I, and this person name is person J, and there is a ATM. Okay, so you need to take out money, okay, from this ATM, and in the ATM only one person can enter at a time. Okay, so now who will enter into this ATM is decided by the value of the turn. Okay, is decided by the value of the turn. So for your convenience, say for example, I'm going to cut this. Okay, so at this moment of time, the ATM is free. Now the process PI wants to enter the critical section. The process PI wants to enter the critical section. Okay, so it has made so process PI want to enter the ATM. Okay, not the critical ATM. So the turn value will be first set to I. Once the turn value is set to I, it indicates that person PI is allowed to enter the ATM. So person PI has entered the ATM, right? So person PI will take out money, okay, and will come out of it. So while coming out of it, it will make this value I to value J. Okay, it will make the value I to value J. Okay, and then it will come out. So what I have done was, in this scenario, what I have done was, first the turn value is set to I. First turn value is set to I, indicating that the person PI wants to enter the critical section, enter the ATM for withdrawing money. So turn value is set to I. Then person will enter the ATM and withdraw the money. And after completing that task, before coming out, it will change the value of turn from I to J. Okay, so indicating that now it's person PJ's turn, and then it will come out. Now when the turn value will become J, so the person J will enter the ATM for withdrawing money. Okay, and it will do its task again. After completing the task, again the value will be set to I. Okay, so when one person goes, okay, while coming out, it change the value and give it to another person. Okay, now here one after another the ATM is being accessed. It's not happening that the ATM is being accessed by two persons at the same time. So this situation is known as a mutual exclusion. Now, but we are talking about Bezier or spin lock. With Bezier and spin lock both means the same thing. Now let me give an example. Okay, so when PI was or wants to enter into ATM, turn will be set to I, and the person PI will be inside the ATM for withdrawing money, and it is doing its task. Okay, so at the same time, okay, when person PJ want to enter it, okay, it will check the value of turn. Okay, its turn is I. So in that situation, it is not PJ's turn, so it has to wait. It is keep on checking. So it is keep on checking the value of turn. So in other words, the person Pj is keep on waiting when this turn value will be set from I to j by process Pi. Okay, so it will keep on checking it. It will keep on checking it here. Strike it out. It will keep on checking when the turn value will be changed from I to j, so that he can enter and do his task. But now currently, but at this moment of time, um, ATM is being accessed by person PI, because it is withdrawing some task due to network error. So it is taking quite long amount of time. So process PJ cannot enter, but it is keep on checking. It is continuously checking in the value of turn has been changed from I to j or not. Okay, this situation is known as a spin lock. So it has spinned. It has keep on checking into this area. Okay, so when from programming point of view, how do you write such kind of code? So while, okay, so I'll just so while I'll just write the code roughly. While tur and turn not equals to j. So if it is not my turn, I've kept semicolon over here. You need to note it down, the importance of semicolon over here. Uh, when you try to write down this code, or when the process PJ try to write down this code, okay, and if this condition is true, the process PJ will be in a continuous loop, because it is not while turn is not equal to j, it should be j, right? It should be j. Okay, so while it is not my turn, this is a process pj. Okay, so process pj will keep on checking it whether it's my turn or not, or whether the value of the turn is equals to j, or in other words, whether it's not equals to j or not. If it is not equals to j, what does it mean? If it is not equals to j, then turn value is I. If it is not equal to j, then very strong value is I. So if it is not equal to j, if it is true, then it will be in a loop, spin lock, because semicolon is over here. If it is true, if this condition is true, okay, the control will be in the while loop itself, because semicolon is here. So this is the meaning of spin lock, and another name for spin lock is busy wait also, because it has been, because the person PJ is keep on waiting for this value of turn variable to be changed from I to j. So this is known as a spin lock or busy wait. So with this explanation, I hope I had made it clear. We'll move ahead. Now algorithm 1. So we'll discuss the first algorithm, and the algorithm 1 basically uses the concept of turn variable only. Okay, now as shown in the described in the previous example, whenever the value of turn is checked, okay, or the turn is set to I or j, indicating that there is only two processes, Pi and Pj. Suppose the turn value is I, that it indicates that process Pi has to enter the critical section. Or if the turn value is j, then process Pj has to enter the critical section next. Okay, so now whenever you write down the code for critical section, solving the solution to the critical section, it has some certain criteria format, like entry section, exit section, critical section, and remainder section. So you can see in this code, for this blue color code is the code for process Pi, and this yellow color or the orange color code is for process Pj. Okay, so this while loop is respect to refers to the entry section code, and this turn equals to j refers to exit section code, and same follows with the j. So this is standard format. So now let us check it out, how this algorithm is designed and how the criteria are satisfied. Okay, so first I'll explain the meaning of this code. Okay, so there is a while loop, okay, while true, okay, while true, and then inside while loop there is a code. Okay, you can even use do while also, do and while, same code up and down. Okay, whichever is applicable to you. Okay, so inside the code you have written turn equal to j. So if process Pj Pj wishes to enter the critical section, so it has to set the turn variable. It has to set the turn variable. Now the working I'll discuss after some time. So the turn is now set to J, which this means that now pre-J can enter it. Again it is checking turn is not equals to I, okay, some reason, and then after when this while condition is true, it will be in a loop. I repeat, when this turn condition is not equals to I, when this condition is true, it will be in a loop. It will be in a loop, the entry section loop, okay. If this condition is true, if this condition is false, then only critical section code will be executed, okay. After completing the critical section code, this is the exit section code, okay. Turn equals to J, so turn value is changed from changed to another variable, okay. Okay, now the remaining portion of the code is remainder, and same is with out here also. Same is with out here. So now we'll try to work, try to understand how it works. Okay? Suppose there is a turn variable, and this turn variable is a shared variable between by process Pi and Pj. And now suppose the turn value is I. Suppose the turn value is I. Okay. When the turn value is I, okay, now let us check it out how it will work. So initially the turn value is I, okay, or the turn value is J, okay. Okay, suppose Pi, what will happen? We'll check it out. Suppose the turn value is J. I'll write it out here, okay. This is TURN, okay. So initially when this statement gets executed for the first time, the turn value is set to J. The turn value is set to J. Turn value is set to J. Now after that process Pi will check, okay, whether it is not my turn. This has to be read in this way. While turn is not equals to, if it is not my turn, because I have told you that whichever turn holds the value, okay, that process is eligible to enter the critical section. So now the currently turn value is J, so turn is not equals to I. It's true. It's the currently the turn value is J. So in that case, if this condition is true, what will happen? It will be in a spin lock, okay. So this is the scenario. So at the same time, okay, when computer executes this, turn is not equals to J. Turn is not J. No, it's wrong. Turn is equals to J. So it's become false. So at this time, process Pj will enter the critical section. Process Pj will enter the critical section, right? So now the process Pj is executed in the critical section, whereas process Pi is in a busy wait, a spin lock in this. Now after executing this, okay, after executing this critical section by process Pj, it will come out of the critical section, and before going to the remainder section, it will change the value from J to I. So turn value is now set to I. So J will be changed now the value of I. So as soon as process Pj will change the value from J to I, as soon as process Pj will change the value from J to I, okay, immediately this condition is true. Immediately process Pi will be eligible now, and when it was checking turn is not equals to I, but now turn is equals to I, so this condition will now become false. So the process Pi will enter the critical section, right? And again after completing the execution of critical section, okay, after executing the critical section, what will happen? Or suppose the process Pi is currently executing critical section, it is process Pj is executing the remainder section, and then again it wishes to enter it, again it will check it. It will keep on checking it. Process Pj will keep on checking it, okay. This busy wait symbol circular. Now After completing the executing of critical section by process Pi will again change the value of the turn into J. So currently it was I, now I will be changed from I to J. Okay. So now when as soon as process Pi change it, this condition will become false, and there will be strict mutual exclusion, flipping of one process to another process. So when Pi will come out of the critical section, it will hand over the critical section, make the eligible make the another allow another process to enter the critical section by changing the value of turn. So there is a strict flip over of turn variable from I to J and J to I, like that way. So in short, so when we can just, you have seen that through this example, when the Pi was executing critical section, Pj was busy in busy wait. Pj was in busy wait or in spin lock. Basically, Pj was not executing critical section. So I can say that mutual exclusion is satisfied. I can say that mutual exclusion is now satisfied. Okay. So this is first thing. Now let us see whether the progress has been satisfied or not. Okay. So let me give a recap of what is the meaning of progress. So progress means progress is a criteria number 2 for solution to the critical section problem. In progress, whenever there is one process who wishes to enter the critical section next, but cannot enter because some other process has not done some task which is not allowing the process to enter the critical section. Okay, I hope you will understand with the help of the example. Suppose this is a turn variable T-U-R-N. Okay, suppose this is turn variable and it has got initially, suppose initially process Pi wishes to enter. Okay, so process Pi wishes to enter. So suppose Pi is now currently executing the critical section. Okay, Pi wishes to enter, it will change the value of turn to I, and then or Pj will give the assign the value of turn to I, and then Pi will enter it. Pi will execute the critical section. At that time, Pj will be in a while loop. Okay, busy wait. Now after completing it, Pi will now change the value from I to J. Okay, I to J. So it will give chance to execute the CS for Pj. Okay, and Pi will come out of it. It will execute the remainder section, and after after coming out of the critical section and changing the value from I to J by process Pi, it will enter into the remainder section and does not wishes to re-enter the critical section next. Does not wishes. So process Pi, once it enters, and next time it doesn't want to enter. It does not want to enter. Right? Pi does not wish to enter the critical section next. Now it is busy executing remainder section code. Now at that same time, Pj has completed the execution of critical section and has executed this code and has changed the value from currently Z, has changed the value from J to I now. So now value of turn is I, right? Now since Pi is not at all interested, so Pi will not wishes to enter. But if process Pj want to re-enter, and this code is with process Pi, right? This code is with process Pi. So it will happen that turn value will be never changed from I to J, because who is changing? For process Pj, Pi was changing, and for process Pi, Pj was changing the code. So you can say that the decision for entering the critical section next for process Pj is influenced by the code of the Pi, which should not happen in case of process progress. Okay, so I'll just show you the meaning of progress. If no process is executing in the critical section and there exists some process who wishes to enter the critical section, then the selection of process that will enter the critical cannot be postponed indefinitely. Here what is happening? The which process will enter the critical section, that decision is being influenced by another process, right? So I'll just go to the paint, not this one, yeah, this one. So here Pj wishes to enter but Pi does not wishes to enter. Okay, now Pj wishes to enter and this criteria can be satisfied only by Pi. Since Pi is not interested, so it will never execute turn equals to z. It will never happen this. So this code will never happen if Pj is not interested. So the decision for Pj to re-enter the critical section next is influenced by the code of the Pi, which should not happen in case of progress. And since Pi will never execute turn equals to z because it doesn't want to enter, so Pj will never enter the critical section although it wishes. Okay, so this decision will never happen because turn equals to j will never be executed by process Pi because process Pi is not interested in entering the critical section next. Okay, so from here we can make it out that progress is not being satisfied. Okay, progress criteria has not been satisfied. Now let us check on the bounded waiting. Okay, so what do you mean by bounded waiting? Bounded waiting means when there is one process who wishes to enter the critical section and there is another process who also wishes to enter the critical section, then you can allow at max one process to enter the critical section and come out of it, and next time it should get a chance. But now you have seen just now in this example, suppose the process Pi has entered the critical section and has exited it by executing this instruction and is executing the remainder section code and does not wishes to re-enter the critical section next, does not wishes second time. Okay, but Pj want to enter the critical section again and again. Okay, so now here the decision for Pj to enter the critical section next has been waited for indefinite amount of time. So Pj has to wait for infinite amount of time until Py interest comes back, which is definitely not going to happen. Okay, based on this scenario. Okay, so obviously bounded waiting will also not be satisfied. Okay, so for algorithm 1, mutual exclusion is being satisfied, progress and bounded waiting is not satisfied. Now let us have a look on the algorithm 2. Okay, so let's now have a look on the algorithm 2. So in case of algorithm 2, the author uses the flag variable only, flag. This flag is a boolean variable. Boolean means the content of this flag will be either true or false. If the flag variable flag of I, okay, so this flag of I, this is flag of j. Okay, so flag has two memory. One memory is for your I, okay, and another memory is for your j. Now if flag does if flag of I is, if flag of this memory location is equals to I, then it means that process Pi wishes to enter. It just wishes. Okay, whether it is allowed or not, that is decided later on. Whenever process Pi wishes to enter into the critical section, it has to set this memory location true. So this ith memory location should be true. Again, when the process Pj wishes to enter the critical section, okay, in the j memory location it should make it true. So true and false in the respective memory location of I and j, okay, will decide who is interested. So if Pj is interested, then in the Pj's location, I'll just make it very clear. This is your flag variable. Okay, this is for I location and this is for j location. If process Pi wishes to enter the critical section, then make it true. If process Pj wishes to enter the critical section, then make this true. Okay. If it does not wishes to enter the critical section or has completed execution critical section, then after coming out of the critical section, make it false. Similarly, if Pj also has recently completed the execution critical section and want to come out of the critical section, it will first make it false and then it will make it. So the value true and false for process Pi and Pj will decide whether Pi is interested or Pj is interested. It is just the interest, it is not the decision, right? So with this we'll move ahead. Now when process Pi, okay, so before I go about the algorithm, uh, okay, it has to do two tasks. Okay, it has to do two tasks. Whenever a process want to enter the critical section, it has to do two tasks. First, it should show the interest by setting it true. Another, you need to check whether somebody is interested or not, whether some another process is interested or not. So it has to do two tasks. So whenever any process is interested in entering the critical section, it has to do two tasks. One is it has to set the in the respective memory location true. Okay, if Pi want to enter the critical section in the flag of I, it should make it true. That is task number one. And task number two is to check whether somebody is interested or not. If somebody is interested, then let them go about it. Okay, my handwriting is very good. I'm drawing with the mouse. So it has to do two tasks. You please keep this in your mind. Okay. So initially the content of flag variable for both memory location is false. Now process Pi wishes to enter the critical section. Process Pi wishes to enter critical section. So it will make this false to true. Okay, so it will make this false to true. So it will make the false to true, and this has been completely executed. Now next it will execute this. So while flag of j is equals to true, means if flag of j is interested, let the flag of j will be executing critical section. If flag of j means if process this indicates if Pj is interested, then let Pj go through it. Okay, but here in this case flag of j is equals to true. No, currently flag of j is false. So this while condition is false. If while condition is false, what will happen? Py will be executing the critical section. So now Pi will execute the critical section. Okay. So when Pi was executing critical section, what Pj will be doing? Okay. Now suppose the Pi is executing critical section. Now let us check it out here. Okay, Pj is now interested, so Pj will make the flag of j equals to true because Pj is now interested. Okay, now it has shown the interest. Pj has shown the interest. Okay, and then after showing the interest, it will check here. So this is a completely executed. Okay, you can see over here. Now Pj wants to check whether somebody is interested or not. So while flag of I is equals to true, so we can see flag of I is true. Yes, the condition is true. If this condition is true, it will be in a spin lock. So you can see over here mutual exclusion has been satisfied because since Pi was executing critical section, Pj was not allowed to go through it. So yes, very good. Mutual exclusion has now been satisfied. Okay. So this is all about the mutual exclusion part. Now let us look it from different angle. Okay, let us look it from now different angle. So mutual exclusion is satisfied. You need to keep this in mind. Now let us check whether the progress has been satisfied or not. Okay? So progress means, I repeat, whenever any process wants to enter the critical section, nobody should influence the other process decision. Okay. So having said this, let us go through it. Now suppose Pi want to enter the critical section, it will make it the from false to true. So this is done. Now again it will check it out. Okay, again it will check it out. Okay, yeah, pi can now enter the critical section. Good. Okay, now it will make it false. Okay, and after that it is not going to re-enter it. It is not going to re-enter it. Fine, it is not going to re-enter it. So now it is again false with the help of this code. With the help of this code, it is now again false. Now once it is false, now again second time pi don't want to enter the critical section. Now what pj will do? Okay, pj will enter the critical section, okay, by making it true. So it will first make it true, again check it if flag of I is equal to true or not. No, it's false right now. It's now false right now. Okay, so if it is false, pi will and pj will enter the critical section. If pi is entering the critical section, if pi is in, pi doesn't wishes, so pi is not interested, but pj was interested. It has made it true, and the condition of the flag is also false. So now eligibility for process pj is satisfied. So pj will execute critical section. Then after that, after completing the execution, pj will make it false. Okay, pj will make it false. Okay, and it will execute. Now again it want to re-enter it. It will again for re-entering the critical section, it will make it again make it from false to true. So this memory location again it will make it true. Again it will check flag of I is equal to true. So again the condition while loop is false. Although okay, while loop is false. So if it is false, again the criteria for pj is satisfied. Again pj will enter the critical. So now here you might think that okay, progress is now weighted because we have followed the same procedure for our algorithm 1. But let us look at the same thing in different angle. Okay, let us check it in the different angle. Suppose for the first time pi have executed flag of I equals to true. So pi has shown the interest. So true. Now since your computer is always execute the instruction time multiplex fashion or interleaved fashion, so this code is executed at time t1 for pi. At time t equals to, suppose this code is executed instead of this while loop code. Suppose this code is executed of process pj, okay, and pj also wishes to enter the critical section, it will make it true, right? Now after that, whichever you selected, this or this, okay, so say for example I select this code, while loop code. Now it will check while flag of j is true, so process pi will think that okay, pj is interested, so I should wait. So it will be in a while loop. So in the next time equals to 1 2 3 4, again pj will also check, okay, whether pj is interested. Yes, it is interested, true. Again it will. So it is what is happening out here. So pi is waiting, pi is thinking that pj is interested, and pj is thinking that pi is interested. So nobody will enter the critical section, both will be in a spin lock. So basically a decision is not being made in a finite unit of time, so progress will not be satisfied. So that's how progress criteria is not satisfied. Since progress is not satisfied, so we did not check for the bounded waiting also. So this is how algorithm 1 and algorithm 2 works. Now going to the last portion of the algorithm, which this algorithm, algorithm number 3, uses the both variable flag and turn variable for solving the critical Peterson solution, and using this all three criteria is satisfied: mutual exclusion, progress, and bounded waiting. So I'll just show you the glimpse of it. Okay. So whenever the process pi wishes to enter the critical section, it will make it true. Now I am interested, so I'll make it true. Okay. Now it will change. It will now set the value of turn equals to j. It will set the value of turn equals to j. Then check whether this statement should be read in this way. Whether it is not, whether it is j's turn or not. Whether if it is j's turn, and if j is interested, if it is j's turn, and if it is interested. So flag means interested, turn means who is going to enter next. So if the turn value is j, or and if j is interested, if both condition is true, so this should be true, this should be true. So result will be AND operation, true true, answer will be true. See, if both the condition is true, then the entire result, entire relation expression will be true. If this both condition is true, then pi will be in a spin lock, right? So you have to read this while loop in this way. If pj is interested and it is pj's turn, then I will wait, I will be in a spin lock. Okay, so at that time when this pi is in spin lock and pj is checking over here, let us check it whether it is satisfying the criteria or not. Okay, so now you assume that flag of j is equals to true and turn is equals to j. Okay, now flag of I, okay fine, pi is interested, pi is interested. Okay, so pi is interested, it can be true. Okay, now since turn can take only one value, j or I, so if this is true, so it will be obviously that turn is equals to I will be false, right? So turn is a single valued variable which can hold only one value, I or j. So if this condition is true for pi, if this condition is true, that is very obvious that for this pj this condition will be false. So at that time turn can take I or j. If this condition is true, this condition will be false due to this. Okay, so basically mutual exclusion is holding, and if you try to analyze the way that I have told you for algorithm 1 and algorithm 2, the progress and bounded weighting will also be satisfied for the algorithm, that you can explore it on your own. Okay, thank you so much. So if there is any questions, you can please post it. Okay, just repeat, I'll just give a review of it. We have discussed the algorithm 1, okay, which only satisfies the criteria for mutual exclusion, progress and bounded weighting not satisfied. Algorithm 2, it satisfies only the mutual exclusion, progress it is not satisfying, bounded weighting not checked, not necessary checked, and it uses the concept of flag variable or boolean variable. Next is the algorithm 3, which uses the both variables, boolean variable and turn variable, to find out the solution for CS problem, and it satisfies all three criteria. Okay, and this while loop has to be read in this form. If suppose this code is for process pi, you have to read this while loop in this way. If it is pj's turn, I'm talking from the pi's point of view. If it is pj's turn, or if pj is interested, flag of j if it is true, if pj is interested, and if it is pj's turn, if both are true, then I need to wait means pi need to wait. Okay, so since turn can take only one value, I or j at a time, if this condition is true, obviously this condition will become false. Okay, so like that way you need to explore it on your own, and in addition to it we have discussed the technical term like spin lock and busy wait. Okay, so that's all for today. Thank you so much. If you have any questions, you please post it. Thank you so much.